back. I'll give the second talk. And I think this is the first time I'm talking officially about something we call nested pfaffian functions. So the motivation behind this notion of pfaffian functions is that working with Gareth Jones for some years now, we had the suspicion that the usual notion of Pfaffian chain isn't quite as general as what Chovansky calls Pfaffian functions in his thesis, or in the corresponding book on phenomials. And for a long time, that was just a suspicion. And the recent result of Scanlon and Freitag actually confirmed that. So I want to talk a little bit about that. And I also want to talk about how one could, or suggest, a more general notion of Pfaffian chain that actually comes out of Chovansky's work. And yeah, we'll take it up. So I'll start with the Pfaffian chains as most people know them. Right, so a Pfaffian chain is a tuple of functions. Let's say k-tuple functions defined on some, for me now in this talk, it's going to be a box that contains the origin. Okay, and so that will take values in Rk, where B, so let's say in Rm is an open box. Containing the origin. Please let me know if I'm writing too small for the people online. Okay. So, of course, one could take other sets than boxes, but I just want boxes. I want a set of neighborhoods of the origin that's very simple. Right. So in this case, boxes. Okay. So this tuple F is a Pfaffian chain of length k. Right, so that's where the k here comes in. If all its partial derivatives of all the partial derivatives of every map in the chain are satisfy a differential system of differential equations that's triangular in the following sense. So there are polynomials Pij, right, and they have, let's see, we have m variables here and k variables here. Yes, so these Pij's yeah, I don't want to write down the number of variables. It'll become clear when I write the system, right? Such that the jth partial of the ith function f in this chain at a point x in the box, okay, is given by the Pij polynomial evaluated at x, and where you're allowed to plug in f1 of x up to fi of x, right? The fact that we stop at fi of x is the triangularity in the system that I'm referring to. So this is right for all I and j, and for all x in the box. Right, so this is your classical Pfaffian system with polynomial equations. Okay, and so generally, today I'm just interested in these kinds of Pfaffian chains or their germs at zero. I'm not interested that their behavior at infinity. Okay, I'm interested in the germs of f at 0. Right, so from that point of view, what I'm interested in here these are all functions that are definable in our sub n in terms of homominimality. Right, this is already settled. The fact that these guys are polynomials means these functions are real analytic. I'm not interested in their behavior at infinity or at the boundary of the box, which is the same thing. Okay. So a couple of examples that I want to keep track of along for the talk. If you have a polynomial, p of x is a polynomial such that well, okay, we can say that p of x is never 0. P of x is not 0 in B, or I can just say the germ of p of x is not 0 at 0, right? So this is the same thing because I can just shrink the box. Okay. So in this situation, the reciprocal of P is pfaffian. Meaning it is just a pfaffian chain of length 1. Okay. And that's obvious because the derivative of this, right, is going to be using the chain rule. What does it satisfy? The derivative, oh yeah, well, any partial derivative is equal to minus the derivative of P times 1 over P squared. Right, so that's a pfaffian equation right there, 1 over P. All right, so that's one thing I want to keep track of. We can always incorporate rational functions like this into chains. Yeah, the usual right chain, the most famous chain, right, are the chains of the form x, second iterative x, third iterative x, and so on, up to the case iterative x. So this is a pfaffian chain. Or maybe I should say this right, where x by denotes the ith compositional iterate of x. Again, at 0, of course, this is a chain of restricted analytic functions. Okay. And so in general, right, if you do have a solution to a system like this, right, the functions fi, they are all real analytic, so they have a Taylor series that is convergent at 0. Okay. So in general, these pfaffian, oh, right, and the pfaffian function is just a member of a pfaffian chain. I'll refer to the individual functions as pfaffian functions. These pfaffian functions have convergent Taylor series at the origin. Okay. So far, so good. Everybody agrees? All right. Okay, so there's lots of questions around these functions, of course. The big one is when we are interested in the full Pfaffian chains, not just their restrictions or their germs at zero, right? The question is, yeah, well, you can look at R pfaff, which is the expansion of the real field by all Pfaffian chains, not just the germs, but by all Pfaffian chains, possibly defined on the whole space, like the exponential function. Right? What can we say about that? We know it's so minimal. What we don't know about it yet is whether or not it's a model complete in the language of Pfaffian chains. Those are open questions, but I don't want to get into those questions at all today, although they are somewhat related to what I'm trying to say. Okay. So like I said, I'm interested today in just their germs at zero. And we have this suspicion, or we had this suspicion that these germs at zero aren't quite as general as what Chovansky called Pfaffian functions, even locally, as germs at zero. Okay. So let's make that a little more specific, right? So kind of as an example too. So let's make this a kind of example. So look at the function eta, which is defined on the interval 0, 1. Okay. Takes real values. And this is the function eta of x is j of ix. Okay, where j is the usual j function for elliptic curves. Okay. Right, so this j function is a complex holomorphic function, right, defined on its very characteristic domain that includes I times this interval. And on this I times this interval, it's real value. So I'm interested in the real function, right, which is this eta here, defined on the interval from 0 to 1. Now, okay, it's only to the right of 0, right? So the question, right, in terms of the notions of Pfaffian germs here, right? The question was, is the function eta of x minus a a Pfaffian function in the sense there for any a between 0 and 1. Right? It's the germ of this function, Pfaffian in this sense. Okay, so here is what we knew for quite a while, and maybe probably wasn't just us. This might be something that people have discovered a few times all over the years. So let's fix this number a between 0 and 1. Then you can find positive b, and you can find a Pfaffian chain of a certain length. Right? I'm not going to go into the details, but it's not a very long one, maybe length 3 or 4. Okay, the Pfaffian chain F this is defined on the interval from minus b to b with real values, okay, such that fk is close to this function, to the j function at a. In fact, fk is injective. Okay, so it has a compositional inverse. And its compositional inverse is 8 out of x minus a. Right, so yeah, this is a fairly elementary calculation. It's based on the differential equation that the J function satisfies. Right, you have to unravel all that a little bit to find this Pfaffian chain. And so looking at that, right, one was always hoping that maybe one can just do some kind of trick to also find a Pfaffian chain for this one directly. We weren't able to do that. Okay, so, but we knew this. Okay. So this is close to being Pfaffian. I wouldn't call it an example, obviously, because it doesn't say that it is an example. Okay. And in fact, that's the result that that was recently, well, part of it is published and the other part is on the archive, right? That's paper, right? But this is due to right talk, but based on a result, on a joint result of him with Scanlon. Okay. That in fact, the germ of x of 8 out of x minus a is not Pfaffian. Okay. So it's not Pfaffian, and this is for any a between 0 and 1. Right, so it seems like with this lemma, we get very close, right? Except for inverting the function. We're right there, almost there. But we never were able to get to Pfaffian. And now they proved by different means that in fact it isn't Pfaffian. Right? So this proof is based on differential algebra, more precisely the model theory of differential algebra. It's not trivial at all. But it can be, well, it can be maybe best described as a version of Galois theory for this type of equations, right? There's a question. Do you mean 8 out of x plus a? What did I write? Oh, yes. I believe that's what I do mean. Yes. Okay. Anywhere else? Here I plus, yes. Right. Although I think it doesn't really matter because the other one is just f of minus the other. There. Shouldn't really matter much. Okay. But yes, this proof is, so it's based on the model theory of differential algebra. It can be viewed a bit as a version of Galois theory for this type of differential equations. Okay. Sorry, my tablet just fell asleep. I hope it's not that boring. Aha, so this was an indication, right, that maybe our suspicion about the notion of Pfaffian chain not being quite the same as the one Hovansky had suggested. Maybe that's confirmed through this, but of course, in order to do that, we have to understand a bit more what a Pfaffian function in the sense of Hovansky actually is, right? And then they have to see whether or not the J function is one of those. So that gets me to part 2 of the talk, and I'm going to go over here. So okay, so and so I have to describe a little bit for those of you who have seen that before. Sorry, but I have to do this again. Right, the setup that we had, or that Hovansky had in his thesis about Pfaffian functions. So Chovansky's approach, right, to the triangularity of the systems of equations was a geometric one. There's a nice geometric interpretation of what this triangularity means. And it uses the language of differential geometry. Okay, so instead of talking about differential equations, you talk about distributions of vector space, right? Vector space distributions on Rn. So I have to make a little detour into that. And then out of that will come a notion of what we call nested Pfaffian chains, which don't look quite the same as the Pfaffian chains that we had on the board here. So again, right, let B be a box that contains the origin. Now I'm going to say it's in Rn, right? The idea is that Rn roughly corresponds to n roughly corresponds to m plus k over here, roughly. It's not quite the same. Okay. So in the geometric point of view, you start from the system of the differential equations, and I'm talking about instead these distributions of vector space. Okay, so a nested distribution, right? The nestedness is what corresponds to the triangularity of the system over there. Nested distribution on B is a tuple D. There's going to be a D1 up to dk, right? So the k still has kind of the same meaning as over there, kind of the length or depth of the nestedness. Okay, where di, so this is going to be a map from the box, which assigns to every point a vector subspace of Rn of dimension n minus I. Okay, so in other words, the values are going to be in the Grassmannian of n minus 1 vector spaces, subspaces of Rn. Okay, so that's a fairly abstract thing, but it can be represented right by. It can be represented unique. Every such space can be uniquely represented by the matrix of the orthonormal projection on the orthogonal complement of the space in question. So in other words, you can represent every point in here by a matrix, n by n matrix, which so right. So we can consider this as a subset of our n square if it helps. In fact, even an algebraic subset of that Rn squared. So this is what's called an n minus I distribution on B. Right, so you have this distribution, and the nestedness refers to the fact that B1, right, that's the biggest one, because its spaces all have codimension 1, right, and then D2 has codimension 2 spaces, and they should all be contained in the corresponding D1 codimension 1 space, and so on. That's the nestedness. Okay, so I mean, this means at every point X in B. This whole. Does that make sense? Okay. So,
Patrick, may I ask a question?
yes.
So in the second point of view, Ari here. So in the second point of view, you have a bound on the length of your chain, right? K cannot be more than n.
Yes.
Whereas the first, in theory, you could have very long chains, or maybe it reduces to the same thing.
Yes, that's right. Yes, in theory, you can have very long chains. Yep, that's correct. So what this will mean, as you will eventually see, is that if the chain, the only way that we can connect the Pfaffian chains in the classical setting to the nested Pfaffian chains that I will define over here is by choosing the n there large enough, right? Like I said, it would have to be m plus k.
Okay. Okay.
All right.
Okay. Thank you.
Yeah. So that, think of it this way, right? The n over here on the left is m plus k over there. So it's just a n equal to m plus k. Maybe that helps.
Yeah. Okay.
That.
Yeah. Great. Great. Thank you.
Yeah. Okay. All right. So these distributions, right? They represent the system of equations. What represents the solution, or the Pfaffian chain, is what we call the solutions to the distributions. And these things in differential geometry called leaves. Okay. So, and here we of course talk about nested leaves of the distribution D, the nested distribution D. So this is also a tuple. It's a tuple of manifolds where each VI is a leaf of the distribution DI. So what is a leaf of the distribution? Right, the distribution assigns to every point in n-1 dimensional vector space. And a solution will be, or a leaf, will be a manifold whose tangent space at that point is the space assigned by DI at that point. Okay, so it's tangent at every point to DI. Leaf also means that it's a maximal connected such solution. If you've done differential equations, you know one is always looking for the maximal solution, right, on the maximal interval or maximal connected set or something like this. So this is what this is referring to. Okay. So leaf means manifold whose tangent spaces are given by this prescribed distribution. Yep. Oh, yeah, yes, right. One. Not more than one, no. That's right. Okay, so D1 is codimension 1, D2 is codimension 2, and so on. And they're contained in each other. So DI has codimension 1 and DI minus 1. Always, yeah. So the same is true for these manifolds. Right? So these are manifolds of dimension n minus I. Oh no, you could, of course, yeah, you could talk about bigger jumps, but we can't do that. You'll see why, because so well, let me give you a couple of examples first, and then right. I mean, it's kind of hard to give examples that are not pathetic, but what is this when k is equal to 1? So k equal to 1. Well, in that case, right, we just have one distribution. Oh yes, how about n equal to 2? So we're just talking about the plane, and we have one distribution of codimension 1 subspaces, in other words, lines. At every point there's a line. So we have a line field. Right? So then D1 is a line field. And, well, what are the leaves of line fields? They're just maximal connected integral curves. And V1 is a maximal connected integral curve. Now, again, maybe you're not quite familiar with line fields, that's not usually how to think, right? But the line field is like a vector field where you forget the length of the vector. You just keep the direction. Okay. If you think about a vector field, of course, a trajectory is a curve that's tangent at every point to the vector field. Okay. But the vector field also gives you a speed prescription at every point. With the line field, we forget about the speed prescription. We just say it's a curve, right? An integral curve is a curve which is tangent at every point. We don't say how fast you travel along the curve. Geometrically speaking, it's the same thing, right? The speed with which you travel along the curve, that does not make a difference to what the curve looks like. Okay? And that's not what we're so interested in. We're just interested in this information here, the direction instead of the vector. So in general, right, the high dimensional version of that is something like this. Make any sense? So right, there is a lot of theory behind this, right? For vector fields or line fields, right? I mean, there are theorems that say if your line field is sufficiently nice, especially if it's C1, that's already good, right? Even less than C1 is necessary. Then to every point, there is a unique curve, right? That passes through it. That's not quite true in higher codimension, right? So we could have n equal to 3 and k equal to 1, in which case we have a plane field, and there are plane fields that have no solution. Okay, and the question of when you do have a solution can actually be answered. That's known as Frobenius theorem. There's a condition on the distribution that tells you whether or not to every point you have a solution. Okay, but I'm not interested in the existence. I'm just saying if I have something like a V that is a solution of such a D, then I want to do something with it. Right? I'm not. If it doesn't exist, then to me it's not a problem. Right? Then I have nothing to say. Okay. And so what we are interested in, though, is not something that's, well, it could be, yes, right, a single distribution of codimension 1, that is possible. We are not interested in a single distribution of codimension 2. Right? If something of codimension 2 arises, it should be tangent to another distribution of codimension 1, right? And my solution to the codimension 2 thing should be inside a solution to the codimension 1 thing. Okay. All right. So let's fix D and V. All right, so a nested distribution on the box B, like over here, and the nested leaf V for that distribution. Okay. So not all of these distributions are nice, and right, one of the key definitions that appear in Chovansky's work is a definition that guarantees that my solutions are nice. Okay, and that is okay. He had a different name for it, but this has evolved a little bit over the years. And I'm going to use the following definition. So I want to, right, Chovansky first realized that's condition is good to work with. Moussu and Roche reformulated it slightly. And then with Lyon, I took up Moussu's definition and made it nested, like in this setting here. Okay. But it's all really already contained in Chovansky's setup. So we call V a nested roller leaf. if, well, if, so remember, right, each VI is of codimension 1 in VI minus 1. So the only problem is I do need a V0 for this definition to make sense, the D0. So, well, D0 should just be the constant assignment of the full space to every point. And V0 should just be my box. Right. That should work. I mean, the box is a manifold with tangent space equal to D0 at every point. Okay. So then what we have is that, so if with this definition, every VI has the Rayleigh property, I will define what that is. In VI minus 1, which means the following. It means that if I have a C1 curve in VI minus 1, which intersects VI in 2 points, then that curve has to be tangent to DI at some point. Okay, so if gamma from 0, 1 into VI minus 1 is a C1 curve, and then to say that it intersects VI in 2 points, let's just say it like this, such that gamma of 0 and gamma of 1 are both in VI. Then there exists some t, some time between 0 and 1, where this curve gamma is tangent to the distribution di. So what does tangent mean? There exists such a t where for the gamma prime of t, right, the tangent is expressed in terms of the tangent vector gamma prime, it belongs to the space defined by di at the point gamma of t. Right, so gamma prime is tangent to that plane or subspace. So that's what it means. All right, so this is a little mysterious, of course. So here's a couple of examples. Again, for the examples, I have to make this very simple. Right, I will just do this in the plane. Right, but VI minus 1 is the bigger one. Oh, yeah. Right, so VI has codimension 1 in VI minus 1. Okay. Aha, so let's see. One example, so both, but these examples are both in the plane, so where k is equal to 1. Okay. And even then I have to cheat a little bit, because in the plane, well, yeah, I have to cheat a little bit just to explain the condition here that I mentioned. Okay. Aha, so the graph of exponentiation, the graph of x, this is a, well, it's, of course, it's not nested because it's just a single thing, right? So it's what we call a Rayleigh leaf of the distribution that derives from the differential equation that x satisfies, right? Of the one distribution on all of our two derived from the fact that x prime is equal to x. Okay. the differential equation, what's the distribution? You can figure that out. Right? But why is this a roller leaf? That's what I want to point out, right? So we have, well, yeah, of course, the exponential function, right? Its graph doesn't really cover much on the right side that I can show. The point is that, so this guy here is going to be a Lie of a line field. But the line field comes from this differential equation. Okay. But it's also the graph of a continuous function defined on the entire line. Right. And so this graph of a continuous function, the complement has two connected components, everything above it and everything below it. Right? Each connected component has the graph as its frontier. This is to say that this curve separates the plane topologically. Aha. So if you have a curve, a C1 curve, right? So it goes a little bit further and then does something here, right? Who knows? Which intersects in 2 points. Okay. It will have to be tangent somewhere. I mean, you can just look at it, at the picture, right? Yeah, you can see a bunch of points where it's going to be tangent, more or less, right? I mean, I don't know exactly what the line field looks like, but probably around here, right? It's going to be tangent. And then maybe again here, and possibly again, why not there? No, that doesn't look right. Here maybe, right? There's a couple of tangency points, but there's at least one. Okay. And this can actually, right, this can be formalized, right, just by using the usual fact that you separate the plane. It's a little bit of differential topology, right? So this is what Chovansky calls his Rolle lemma. Right? It's a version of Rolle's theorem, but not for where instead of having just a C1 function that's somewhere that intersects the horizontal line in 2 points, which has to be somewhere tangent to a horizontal, right? Replace the horizontal line by this graph of x, the horizontal line field by the line field coming from this equation, and then do the same proof using the intermediate value theorem to show that there has to be a tangent. Okay, so this is now known as a version of the Rolle-Chovansky lemma. Okay. So what does not satisfy this Rolle property? So I have to cheat a little because in the plane, it's actually hard to find counterexamples. Okay. Counterexamples in the sense where you do have a distribution on a box in the neighborhood of the origin. Right, so my counterexample is not quite a counterexample, but it explains a little bit why the Rolle property is the right one. Okay, so if you look at a vector field or line field, there are linear ones that have integral curves that are spiral, right? Something like this. I'm sure you've seen many of these, right? The difference is such a vector field cannot possibly assign a line at the origin, right? It has to be singular at the origin. But, okay, that's a different story. Right? I just want to explain, right? This spiraling thing is excluded by the Rolle, does not satisfy the Rolle property. I mean, just look at this C1 curve, right? Intersects here and here, right? But it is never tangent to the field, because that field is never vertical. Okay. So it does not, this is not Rolle. like I said, it's a bit of cheating because I can't quite produce a counterexample where I have in fact, that is a deep theorem. There is no counterexample when they don't have a singularity at the origin. Okay, it's known as Havlicker's theorem, or maybe there's other versions of that too, or that implies. Yes, in particular, in 2 dimensions, you can conclude that this is not, you can't get a counterexample without a singularity. But it explains what the Rayleigh property does, okay, or avoids encountering. Oh, I'm not getting very far. Okay, but the problem is when you start nesting things, right? So now, for the nested Rayleigh leaf, we are doing this inside, right, repeatedly, all codimension one inside each other. And even if right, the first leaf that you have, the V1 leaf, okay, it might be fairly nice, but you may not be simply connected. There's no reason for it to be simply connected. And if it's not simply connected, it's not as simple as the plane. Then I do not need a singularity to create something like this at the next level, right? So what in the picture here, the singularity that causes this problem here in the picture, it can appear in the nested version simply because V1 wasn't simply connected. Okay. So then we really need this Rayleigh property to exclude the spiraling happening. So that's roughly how to explain why we need the Rayleigh property. Turns out the Rayleigh property is exactly the right property you want. Okay, it's still the best way to characterize non-spiraling or, in fact, for that matter, tameness. Okay, so falling asleep again. Okay, so yeah, so it turns out then the right idea, right, to view pfaffian chains somehow in this language here is to consider nested Rayleigh leaves, right? But they're not graphs of functions. So what happens? What's the connection to graphs of functions of these things? So if you unravel this definition of nested Rayleigh leaf, right? So again, let D and V be fixed. And assume V is a nested Rayleigh leaf. Inside each other, exactly, right? So each one has the Rayleigh property with respect to the next bigger one. That's correct. So we are avoiding this thing of appearing even if they are not simply connected at some stage. Okay. Assume that V is a nested Rayleigh leaf. And let's take, up to translation, I can assume that the origin is in fact in VK, in the smallest one of them, so in all of them. Okay, so let's assume. So locally now, what does this look like? Well, these are all manifolds, so each of them looks like the graph of a function. And at a given point, after a permutation of coordinates, we can have the following picture, right? So after shrinking the box and permuting coordinates if necessary, right? I can describe this nested Rayleigh leaf as a sequence of graphs of functions, right? Or not functions, but maps. There are maps. Let's write it sigma And well, there's going to be a sigma 1, sigma 2, up to a sigma k. Okay, so there are maps, tuple of maps, such that sigma I is defined on the projection of the box B of the first n minus I coordinates, right? Vi is an n minus y dimensional manifold, so it should be the graph of a function of n minus I variables, of a map, right? And it goes into Ri. Okay, each of them. And yeah, we want to say that the image sigma I of B, of the projection, is contained in the projection on the remaining I coordinates of B. Okay, so this is the projection on the last I coordinates. This is the projection on the first n minus I coordinate. Right, so the whole graph is in the box B, like we were saying. Okay, so we can, up to permuting coordinates, we can assume that, in fact, each of the leaves here is the graph of such a map. Make sense? And the nestedness means that the only important, right? So each of these guys here is a tuple of functions, but the only important one is the first one, because the other ones can be obtained by composition with the other one. Okay, because of the nestedness. So the tuple of map functions phi, which just keeps the first component of each sigma I, so sigma 1, 1 up to sigma, what's the last one? K 1, right? Is called a nested pfaffian chain. It's a little bizarre, but this is now, you know, a tuple of maps, functions. Okay. So this is a little bizarre, right? So now we have a tuple of functions. Somehow has something to do with the system, right? And therefore with Pfaffian chains, but we call it nested Pfaffian chain. There's some obvious differences here right away. Right, the first one here is a function of n minus 1 variables. The next one is a function of n minus 2 variables, and so on, right? Fewer and fewer variables. So that's not a Pfaffian chain for sure. Pfaffian chains, all the elements have the same number of variables. Okay, so it's not the same, but it's, right, they also satisfy differential equations because again, they are related to these nested roller leaves, right? That's a geometric interpretation of why we have these systems of differential equations. So if you unravel that, you get the following types of differential equations for these nested Pfaffian chains. Okay, so unraveling, and again, the other components here, they can be obtained from these guys by composition. Right, so there's not, the other components are not important. It's just the first ones that are important. So unraveling the definitions, this takes a little bit of work, but following equations. Satisfied by phi, by this nested Pfaffian chain. Okay, so what we get is we need one definition. If you have a function, right? We have here functions of different numbers of variables. So if you have two functions alpha on pi n minus I of b, and another function beta on pi n minus I plus 1 of b, one more variable, okay? And you want to know that the image of alpha that's the graph of alpha. I was just going to say, I want alpha not to go outside of the box B. So, and the graph of alpha to be contained in the projection pi n minus I plus 1 of B. Here we go. Right, I'm going to define the following type of composition. Define a beta composed with alpha, right, which is going to be a function on of n minus 1 variable. So x1 up to xn minus I. That's going to be beta of x1 up to xn minus I. And then for the last coordinate in beta, I plug in alpha of x1 up to xn minus I. Right, composition in the last variable. Make sense? Okay, so then I can find the partials of yeah, so let's call this guy here phi phi1 up to pk, okay? So again, the partial of phi with respect to the variable j, right? At a point x, well, x is x1 up to xn minus I, okay? This is given by what I call pij again, for the moment. We have to say what that is in a moment, right? Of no, it's pij, which is a polynomial in n variables, right? Which I compose in this sense with the phi1, which in turn is composed with phi2, so iterated composition in this sense. Phi. Yeah, no parentheses. Okay, where? So, yeah, the only thing here is, what is this guy here? Well, I haven't specified anything yet. I just talked about nested distributions. I didn't say anything about what types of they are, right? So what we want, of course, is polynomials like in the pfaffian chains, right? So to get polynomials here, essentially, all you need here is that these distributions, right, are defined as the kernels of a polynomial 1/4 each. Right? So there's a way to make sense of that in terms of polynomials. So again, these can just be polynomials for us. Right? So this is an n-variable polynomial. You can compose that with, in this sense, with the first element here is an n-1 variable function, and compose that again with phi2 and so on down to phi. See, the triangularity is again in this stopping at I here for phi. Right? The further down you go in the chain, the more compositions are involved. Okay, another way to say what this is to say pij of x, and then we have no, I don't want to write it out. It's right. It's all these iterations of this thing. It's I'm just going to make mistakes if I do that. It's the easiest way of writing. Okay. Anyway, doesn't quite look the same. These are actually inherently looking different from what we call the nested adjusted pfaffian chain. So not only is the pfaffian chain different in the sense that here we have different numbers of variables for each of the elements, but these equations are also different. But there's a special case of this, which makes it a pfaffian chain. If it so happens that every one of these component functions only depends on the first n minus k variables, then this is exactly a Pfaffian chain. Right? So no. If each pi only depends on x1 up to xn minus k, then this is a Pfaffian chain. These are exactly the equations for Pfaffian chains in that case. So this notion does generalize Pfaffian chains. It's just that we did not see how we can always rewrite this as a Pfaffian chain. We couldn't do that. We were trying to see if this is possible and couldn't do it, right? Clearly seems a lot more general. Why should there always be why should it always be reducible to something where everything only depends on the first n minus k variable? Doesn't seem to be reasonable. Okay. Well, it turns out that these functions here, eta of x plus a, they are all like this, but they're not Pfaffian. Okay, so that's it. These functions, eta of x plus a, they are an example of functions that are nested Pfaffian because they live in nested Pfaffian chains, but not Pfaffian. Okay, so this is a more general way. Not everything is reducible to Pfaffian chains in this sense. How does one see this? It's actually not so hard. This definition of nested Pfaffian chain is the complete natural thing when you try to solve implicit functions. So if your phi k here satisfies the conditions of the implicit function theorem with respect to its last variable, then the implicit function is a function of first n minus k minus 1 variables, which satisfies exactly another Pfaffian equation, almost of this kind, except that we have a rational function here. That just falls out, okay, from the definition of a chain rule. And the rational function we can take care of by the early example that I mentioned. Rational functions are Pfaffian, so they are nested Pfaffian, right? Anything that Pfaffian is nested Pfaffian. So we may have to enlarge the chain a little bit, right, to accommodate implicit functions, but we can. And so that means these guys here by the lemma, right? These guys are just inverse functions of a Pfaffian chain. Pfaffian chains are nested Pfaffian. Inverse functions can be obtained via implicit functions. So it's all there. Okay. So yeah, sorry, I had to go fast a little bit at the end there, going over time. But the example of the J function essentially leads to distinguishing the two notions of Pfaffian chains. To show that they're really not the same. What that means in other respects, that's still largely open. Right? There's lots of questions that one asks about Pfaffian functions. Maybe they're easier to answer in the nested Pfaffian case. Maybe they're true in the nested Pfaffian case, but false in the Pfaffian case. It's all still stuff we're just starting to look at. Anyways, I'm gonna stop here.